Okay, so in this video I'm going to have a look at what are called stationary points, and in particular we're going to have a look at a local maximum, a local minimum, and a point of inflection. And one type of point of inflection here is called a saddle point. We'll have a look at that later on anyway. Now I have here, I actually have three curves here. This is the first one, and they're all related, but this one here is called, let's call it f of x, just f of x. Now, it's a cubic curve, as you can see, so it goes on forever in this direction, goes on forever in this direction here. This point here and this point here, they're both called the local minimum and the local maximum. Now, this is the maximum, obviously it's higher, this one is the minimum here. Now, there are other points down along here and up along here that are higher and lower than these 2 points, but these two here are called the local minimum, the local maximum. Now, let's just have a look at these 2 points in relation to tangents to this curve. If we take, let's say, this part of the curve here, from here up to here, and we draw a tangent. So I'll just draw one tangent up along here like this. So it's roughly straight, you get the idea. So that's a tangent, it touches the curve here. You can see there by looking at this, any tangent I draw from here up to here will be in this direction. It'll have a positive slope. So we can see there that this this tangent here will have a positive slope, and any tangent up along here will have a positive slope. Now, when we reach the top here, if I draw another tangent, it will be more or less, well, it'll be horizontal like this, and this slope here, the slope of this particular tangent here, will be 0, so m is equal to 0 here. It's a horizontal line, so it will have no slope. So you can see all of these tangents from here up to here will have positive slopes. So this part of the function here is increasing. It's an increasing function up along here. Here the slope is 0. Now, if we come down this side then, this side of our curve, if I draw a tangent down along this way, you can see that this particular tangent will have a negative slope. So this tangent will have a negative slope. And any tangent from here down to here will be pointing in this direction, if you like, so it will have a negative slope. So we can see that since all of these tangents have negative slope, this part of the function here is decreasing. And then when we get to the end here, if I draw a tangent here, you will see that this particular tangent again is horizontal. So the slope of this particular tangent here is also 0. And then as we move up this side of our curve, if I drew a tangent here, you can see that this tangent here is again in a positive direction. It has a positive slope. So any tangent on this side of our curve here will have a positive slope. So this part of our slope here, this part of our curve here is increasing. Okay, so we can see that at our 2 turning points here, our 2 stationary points, our maximum here, this is our local maximum, and this is our local minimum here, our slopes are 0. And that's going to be important later on for finding the coordinates of these 2 points. We'll have a look at that later on. Now, let's look at the next curve that I have here. This curve here is actually related to this curve in that it is the first derivative of this curve here. So if we differentiate a cubic curve, we will get f prime of x, and it will be a quadratic curve, quadratic shape, quadratic function. Now, how does this relate to these slopes here? Well, when you differentiate a function, you get an expression or a formula, if you like, for slope. So if we have a look here, for example, this part of our curve here, where all our slopes are positive, this is related to this part of our curve here. So I can look at this part of our curve just from here down to here. This is related to this part of this curve. And in fact I can draw a line straight down here. Let's see, from this point here down to this point here. These two are related. So we can see this curve here is actually gives us an idea of or tells us the sign of the slopes of our tangents to this curve here. So we can see that from here up to here all our tangents have positive slope, and we can see that all our y values for these points here are all positive. These are all positive values here. So this tells us that all of the slopes on this part of our curve here have positive slopes. When we get to our local maximum here, this tangent here has a slope of 0, and this corresponds to this point here on our first derivative curve, and we can see that our y value here is 0. So this indicates that our slope on our f of x is 0. Now, when we look at this part of our curve here, so let me pick a different color here. This part here now I'm going to look at, this part of our curve down along here, whoops, we can see that our function is decreasing down along here. All our slopes here are negative, and we can see here that that corresponds to this part of our first derivative function. And we can see that all of these y values here are negative. They're below the x-axis. So we can see that all our slopes here will be negative. Okay, and again we can see here that at our local minimum we have a horizontal tangent, slope of 0. That corresponds to this point here on our first derivative curve. Okay, now we're moving into this part of our curve. Let's go to a different color. Let's say we go to green. Okay, so this part here, we can see that our function is increasing and our tangents all have positive slopes. And again, we can see that corresponds to this part of our first derivative curve here. And again, we can see that all of these y values are all positive, indicating positive slopes up here, or increasing function here. Okay, so now let's have a look at what's called a point of inflection. Now our point of inflection is in fact this point here, roughly, on my diagram. It's this point here. Now if you look at my tangents here, here and here, you can see they're all above the curve here. And you can see down here, these two tangents here, in fact all these tangents around here will be below the curve. So at some point the tangents crossed over the curve from being above the curve to being below the curve. And that point, where that happens, is called the point of inflection, and that's here. Another way of looking at it is you have this part of the curve here which is concave down. This part of our curve here is concave up. Where the function, or where the curve, where the graph changes from concave down to concave up, that's called a saddle point. And this is our saddle point here. Okay, so what does that correspond to in our first derivative curve? Well, it corresponds to this point here. This point here. In fact, it's the turning point of our first derivative function, our first derivative curve here. This is our turning point. It's a minimum value down here, and that'll be important when we do our second derivative. We'll have a look at that in a second. So let's continue on then. Now, this function here is our first derivative of our original function. This function here is our second derivative. So this is f double prime x. So when you differentiate a quadratic, you get a linear function. This is our linear function here. So what points are we talking about here? Let's have a look at this curve here. This is our first derivative curve. Let's look at tangents again and slopes again, okay? So if you go from here down along to this turning point here, you can see if I draw a tangent here, if I draw a tangent along here, you can see that this tangent here has negative slope. So that tangent has a negative slope here. Now, here we can see that at our turning point here, if I drew a tangent here, we can see that that tangent there will have a zero slope again, so that m is equal to 0 here. And continuing on up along this side, any tangent along here will have positive slope. So this will be positive slope here. So how does that relate to this function here? Well, if you take this part of our curve here, all our tangents will have negative slopes, and we can see that corresponds to this part of our linear function here, our second derivative. And we can see that all of these y values are negative, indicating negative slopes on our previous function. This point here then corresponds to this point here on our second derivative, and we can see that has a y value of 0, indicating a 0 slope here. And then as we continue on up along here, we can see that our tangent here is, all our tangents along here will be positive. They will have positive slopes, indicating, you can see that all of these y values here are positive, indicating positive slopes here. Now, I mentioned a stationary point earlier, and if we continue from here on up to our original function, you can see that there's our stationary, or there's our point of inflection here. That's our point of inflection. Continue on down. We've derived it first. The first derivative is this point here, zero slope. Continue it on down to our second derivative, and we can see that we get a 0 value here for our second derivative. So in fact, we're going to use that point that if you differentiate a function twice, let it equal to 0, that will give you the x value, the x coordinate for the point of inflection. Okay, we'll have a look at that in a few minutes. Now, the last thing I just want to have a look at before we move on to an example is, we had a point of inflection. It was this point here. There is another type of point of inflection called a saddle point, and it will look like this here. You can see that the curve is pointing downwards here and it's pointing upwards here. So there is a point along here that is a point of inflection, and we'll say it's somewhere around here. This is our point of inflection. This point here is called a saddle point, maybe for obvious reasons, because it might look like a saddle if you like. But it has, if you were to draw a tangent at that point, the tangent here will have a slope of 0. That's the only difference. Now, I probably should have drawn the blue line a little bit flatter there. But you get the idea anyway. It kind of goes up like this, flattens out, and then goes up. It doesn't come back down again, kind of flattens out like this. So you end up with a horizontal line, horizontal tangent there, if you like. Okay, so let's move on to some examples then of how you're going to use this kind of information. So let's take a function. I'm just going to do one example really, and the function that we're going to look at is y is equal to, it's going to be a cubic function, so let's say x cubed minus 6x squared plus 9x plus 9x and then minus 5. Okay, so we're going to have a look at this function. It's a cubic function, so it'll look something like that. And we're going to try and find 3 points, okay, 3 points. We're going to look at our local maximum, look for our local minimum, and we're going to look for our point of inflection. So we're going to find x and y here, we're going to find x and y here, and we're going to find x and y here. Now, first thing I'm going to do is find our local maximum and our local minimum. So let's do that first. So in order to do this, remember if I go back to my my function here, this was the original cubic function that I started with. We can see that at the local maximum and at the local minimum, the slope of the tangent is 0. Slope of the tangent is 0. Now, we know that when we differentiate our function, we'll get f prime x, which is effectively slope of tangents. Okay, so I'm going to take my function, differentiate it, and then let it equal to 0. I want to find the x coordinates where the slope is 0, and there are only 2 points where slope is 0, here and here. So let's do that. Now I'm going to differentiate first, so I'm going to do dy dx. Differentiate y with respect to x, that gives me 3x squared minus 2 6 is 12x plus 9. Now this is effectively, this is my slope function. It gives me the slope of any tangent, gives me the slope of any tangent on this curve. Okay, so I want this tangent here, and I want this tangent here. So I know that the slopes are 0 here. So this is my slope function. So I'm going to let this equal to 0. 3x squared minus 12x plus 9 equal to 0. My slope is equal to 0. What x values will give me a slope of 0? So let's just do that. We need to solve this quadratic equation. So I'll do this the normal way. There are a number of ways of doing it, but this should work out for me. I think it's 3 by 3, minus times minus. So that will give me 3x minus 3 equal to 0, or x minus 3 equal to 0. Let me see, do I have that right? 3 3s are 9, 10, and 12. Yes, that works out, okay. So that will give me then, if I solve this here, I'll get x is equal to 1. And if I solve this here, I'll get x is equal to minus, no, not minus 3, it's actually plus 3. So my two x values are 1 and 3. 1 and 3. So now I know here, I have an x value here and I have an x value here. I won't put them in yet because we have to do a little bit more work with them. Now, to work out what the corresponding y values are, all I've got to do is put these into my original function. Y is equal to x cubed minus 6x squared plus 9x minus 5. So I know that x is 1, so just put it in here. 1 cubed minus 6 times 1 squared plus 9 times 1 minus 5. And I know from doing this that if I put 1 in there, I'll get minus 1. This will be minus 1. So one of my points is x is 1 and y is minus 1. Now that's this one, so now I'm going to do this one here. X is equal to 3, so x is equal to 3 here. Now that will give me y is equal to 3 cubed, this time, minus 6 times 3 squared, plus 9 times 3 minus 5. And I know from doing this earlier that y will be minus 5. So my second point is x is 3, y is minus 5. Now I have my local minimum and local maximum. Now it's fairly obvious here that this is going to be my maximum, and this one here is going to be my minimum, because minus 1 is my y value and that's higher than this one here. However, usually what you're going to have to be able to do is prove or show that this is in fact a maximum, this is a minimum. So the way you do that is, we're going to have to do this anyway to find the point of inflection. We're going to have to differentiate a second time. Now, remember that f prime of x, or f dash x, was 3x squared minus 12x plus 9. When we differentiate it once, this is what we get. We're going to have to differentiate x a second time, our function a second time, so that will give me 6x minus 12. So I'm going to use this to determine whether which one of these is a maximum, which one is a minimum. I'm going to use this second derivative here. So this is what you need to do. I'm going to take our x is equal to 1. This is our first one here. I'm going to put that into this here. So x equal to 1. That will give me 6 times 1 minus 12. Remember, I'm using this one here now. Second derivative. That will give me 6 minus 12, which is minus 6. That will give me minus 6. That is negative, which means it's a maximum. That's the rule. If you put your x value into the second derivative and you get a negative answer, then it's a maximum. It's kind of the opposite to what you might think. If it's a minus, it's a maximum. So we'll put the other one in now. X is equal to 3. So that will give me 6 times 3 minus 12. That's 18 minus 12, which is plus 6. This is positive. That means this one, particular one is a minimum. So, in other words, I've kind of confirmed what I suspected anyway. This one here is a maximum, and this one here is my minimum. This is the local maximum, local minimum. Now, what about the point of inflection then? The point of inflection, let's see if we can find that. Remember initially, if I go back to my original diagrams back up here, I said that if I got the second derivative is equal to 0, that will give me, that if I follow this line up here, that will give me my stationary, or my point of inflection I should say here. So my second derivative must be equal to 0. So let's do that. Let's let the second derivative equal to 0. So my second derivative is 6x minus 12. It's this one here. Let that equal to 0. That will give me 6x equal to 12. That will give me x equal to 2. Now I know that at the point of inflection, x is 2. I just need to find what y is now. How do I find what y is? I just put it into my original function again. So my original function was y is equal to x cubed, excuse me, minus 6x squared, plus 9x, and minus 5. So y will be, x is 2 now, so x is 2, that will give me 2 cubed, minus 6 times 2 squared, plus 9 times 2, minus 5. That will give me point of inflection. I have that done somewhere. Let me see. That will give me y is equal to minus 3. Okay, it works out as minus 3. So my point of inflection is in fact 2 minus 3. So now I have my 3 points that I was looking for initially. So I have, let's see, my local maximum was 1 minus 1. My local minimum was 3 minus 5. This is my maximum. This is my minimum. And my point of inflection was 2 minus 3. So I could sketch that if I wanted to. I mean, I know it's a cubic function. It's going to look something like this. Now I know that my local maximum, this point here, is 1 minus 1. I know my local minimum here is 3 minus 5. And my point of inflection here is 2 minus 3. 2 minus 3. So that would give me, my x-axis will be, let's see, that's 1. So my x-axis, let's say, is here. And the top point here, my y value is minus 1. This is minus 3, and this is minus 5. So I'd be looking at an x-axis rather along here somewhere. So this is x, this is y. Okay, so that's it on stationary points.